In this addendum to lecture 15, we are going to talk about the proof of Cheeger's inequality. It was originally proved actually by Alone in 1986 based on earlier similar results by Dodd-Zook and Alone-Millman. It's named after Cheeger due to a 1970 result of Cheeger where he proved, I guess, the analogous result but in the setting of manifolds rather than good old finite graphs. So let me recap what I've already told you about Cheeger's inequality briefly. So Cheeger's inequality is concerned with this quantity phi sub g, which is the minimum conductance of a graph G. It's the least conductance phi s of any subset S of vertices in the graph. Well, as I mentioned in the lecture, you have to restrict to sets S whose volume is not 0. And at most a half, okay? And remember that the conductance of a set S sort of represents the escape probability for that set S in a standard random walk on the graph. So if a set has small conductance, it's a sort of a bottleneck for the random walk. It's a set of vertices where it's hard to escape from. Okay, so taking a little look here in more detail, this is can also be this minimum conductance can also be written like this, and when you put it in this form, it's almost the same as this ratio as we saw. So it's up to a factor of a half. So the conductance involves the probability that a step in the graph escapes S, condition on being in S, divided by this denominator, which is like the volume of the set S. Okay. And if you're assuming that the volume of the set S is between 0 and a half, then its complement has volume between a half and 1. So if you were to throw in a factor of volume of complement of S in the denominator, it would only change things by a factor of a half, which is not going to concern us very much. And what's nice when you have this volume of S times the volume of S complement in the denominator, that's equal to, I guess, mu times 1 minus mu, where mu is the volume of S. Or you might say, another way to write that is mu minus mu squared. And when you see it in that form, as I mentioned before, this is also the variance of the indicator function of the set S. Okay, so this conductance up to a factor of 2 or a half is the minimum over all sets of vertices S. And now once you have the S complement in the denominator, you just have to rule out S being everything or nothing. It's the minimum over all sets S, other than the trivial sets everything and nothing, of the ratio of the quadratic form of the indicator of S, just up here, to the variance of the indicator of S. Okay, and that's interesting. It's interesting to compare that to, as we saw, this quantity here, which is the same minimization program, the minimization, except it's the minimization instead of over indicators of subsets, you minimize over all functions, all real valued functions f on the set of vertices. Again, excluding the trivial case of constant functions, which would make this denominator 0. And what's nice about that, let me just tidy this up a little bit. What's nice about that is this program here, the minimum of the quadratic form of f to the variance of f over all non-constant functions f, as we saw, is a very simple quantity related to eigenvectors and eigenvalues. Namely, it's the second smallest eigenvalue of the Laplacian of the graph, known as lambda 1. Remember, the Laplacian of a graph always trivially has 0 as its smallest eigenvalue, and lambda 1 is sort of the second smallest eigenvalue. And we saw that in the previous lecture, based on some sort of little calculation or some set of formulas for the quadratic form of f and the variance of f in terms of the eigenvalues of the graph Laplacian, together with the coefficients in f's expansion in the eigenvector basis of the Laplacian. Okay, so we saw given any f, we had on one hand this formula here for the quadratic form of f. It's a weighted combination of f's squared coefficients, where this ith squared coefficient is weighted by lambda I, the ith eigenvalue. And we also saw that the variance of a function f is simply the sum of the squared coefficients of f. So if in both cases we actually exclude the 0th coefficient, the one that is the coefficient sitting next to the zeroth eigenvalue vector of the Laplacian, which is always the constant function 1, and that's because the zeroth eigenvalue is always 0. Okay, so long story short, if you could minimize over any f, which basically means you can make these squared coefficients whatever you want, well, if you were trying to minimize this expression, you sort of move all the squared coefficients mass onto the smallest possible eigenvalue coefficient, which by our ordering is lambda 1. Okay, so this is just a recap, and it says that for this program here, where you're minimizing over all real valued functions f, the minimum is an easy to compute value. It's lambda 1, it's the second smallest eigenvalue of L, and the f that achieves this minimum is what we call phi 1, it's the associated eigenvector. So this program is easy to solve exactly, and hopefully, and this is what Cheeger's inequality tells us, it will serve as a good proxy for this program where we're only trying to minimize over 0, 1 functions f. Okay, and it turns out that, computing this minimum exactly is NP hard. This is the sparsest cut problem for a given graph. But Cheeger's inequality sort of tells us that this minimization problem, which is easy, is a good proxy. So let's take a look at Cheeger's inequality precisely. So here's Cheeger's inequality written out precisely as I've written it in the past. It says we have a two-sided relationship between this sparsest cut value, phi g, the minimum conductance in the graph, and this easy to compute eigenvalue lambda 1. Now one side of the inequality is called the trivial side, or the easy side, and it's this inequality here. It basically just says that if you look at this minimization program here, where you minimize over all 0, 1 valued functions, well, you're minimizing over a smaller set than when you're minimizing over all real valued functions. So the answer, lambda 1, when you minimize over all real valued functions, is bound to be at most the minimizer when you only minimize over 0, 1 functions. Okay, and there's this factor of a half because of this factor a half messing around in the definition of conductance. So that's the easy side of Cheeger's inequality, and really Cheeger's inequality refers to this other side of the inequality. This is the hard side, or the main side, which actually says that lambda 1 is in some sense not too bad a proxy for the minimum conductance. It says that the minimum conductance, phi g, is at most some constant times square root of lambda 1. Okay, so qualitatively this is kind of nice. This side of the inequality says that if the conductance is small, then the lambda 1 eigenvalue must also be small. And this side of the inequality says that, conversely, if lambda 1 is small, then the conductance must be also small. Now, this side of the inequality is not as quantitatively as sharp a comparison. It's best possible, actually, up to the value of the constant. But there's a square root involved. But still, qualitatively, it says this fact that if lambda 1 is small, if and only if the minimum conductance is small. Now, in the there's various slight different proofs of Cheeger's inequality, and depending on how careful you are, you can get a different constant factor here. It's not too important to stress out about this constant. I think in the best proof, you can make this constant square root of 2, and I think in the proof I'm going to give you, the constant will be 4, but I didn't even exactly check that too carefully. The point is just some universal and, in fact, small constant. Okay, finally, as I mentioned in the lecture, Cheeger's inequality is sort of a little bit better than this. If you think about the upper bound, what is it telling you? It tells you that if there's some function f that makes this minimization program small, that achieves this a small ratio, lambda 1, then there actually has to be a set with also a set of vertices s with small conductance, okay, where small gets changed up to the square root. And Cheeger's inequality's proof is actually very constructive. It's very, well, constructive, as I say. So, as I mentioned, we can phrase it as follows. Let's say you have just any real valued function f on the vertices, and again, it should not be constant, it should not have variance 0. And let's imagine that it achieves a small value for this minimization program up here. In other words, let's imagine that its quadratic form value, this e of f, is quite small compared to its variance, and quite small means up to a lambda factor. Okay, so in this hypothesis, you can take f to be phi 1, the eigenfunction or eigenvector associated with lambda 1, in which case you can take lambda to be lambda 1. But the theorem, in fact, tells you, you don't have to start with the absolute minimizer f. Any f that achieves like a small value, you'll be able to turn into a set of vertices whose conductance is qualitatively about as small. Okay, so what the stronger version, or the constructive version, says is, you give me any f that makes this program small, whose quadratic form is small compared to its variance, and the theorem will give back to you a set of vertices S with small conductance. So its volume will be between 0 and a half as desired, and its conductance will be at most some constant factor times square root of, this should not say lambda 1, it should just say lambda, whatever this lambda is. Okay, so whatever amount lambda your minimizer or your approximate minimizer f achieves, you'll get a comparably small to a square root conductance set. Okay, and to get this statement up here, you just take f to be the minimizer, which achieves minimum value lambda 1. Okay, and not only that, it's not just that the set S exists, there's actually a pretty straightforward way to derive it from F. In fact, the set S will either always be what I would call a super level set or a sublevel set of F. So what does that mean? It means there will always be some value, real value t, such that now if you take this real valued function f and take all the vertices where f has value at least t and try that as your S, that could potentially be like a set S of reasonably small conductance. And the theorem, in fact, will show that there'll always be some value of t such that either this idea, taking all the vertices where f's value is at least t, or the opposite idea, taking all the vertices where f's value is at most t, one of these two, and for one value of t, you'll get a set of the desired small conductance. Okay, so practically speaking, you can just try all values of t, of which there are really only n plus 1, because if there's n vertices, f only takes on n values, so there's only sort of n plus 1 relevant intervals where t can be. Okay, so this gives you a very nice, in fact, constructive way of taking a function f, achieving a small Rayleigh quotient, as this quotient between the quadratic form and the variance is sometimes called, and converting it to a set with small variance. Okay, so now that I've recapped Cheeger's inequality, let's go on to the proof. And I should mention, well, let me say two things here. One, this set, I'm going to use some shorthand for it. I'm going to write it as f greater than or equal to t. Okay, and I'm going to use analogous, notation like f less than or equal to t or f less than t. It's funny, but this is going to denote a set of vertices. Given a function f, it's the set of all vertices u, where f of u is at least t. I'm also going to not explicitly prove this in fact statement. It'll just be sort of obvious from the proof that we're going to construct this set given like the function f by taking either a super level set or a sub-level set. Okay, so I'll leave that to you to verify as the proof proceeds. Okay, so let me first, before diving into the proof, talk about the idea of the proof. And the idea of the proof is kind of to compare to like a kind of calculus situation, if you will. So I want to sort of imagine plotting f, at least f's values. So the vertical axis is going to be the reals, and the horizontal axis is going to be v, the vertices in the graph. So this doesn't exactly make sense. It's only an idea. Actually, it more or less makes sense if the graph G in question is a path graph, okay? In which case, the vertices just look like a long path, and that sort of looks like the real line. Sort of like this. And let's imagine that we sort of plot f's values. Maybe they go like this. Okay, I guess in this picture, f's values are all non-negative. They don't have to be, but anyway, let's imagine f's values look like this. And now remember, how does Cheeger's inequality work? It's sort of, you imagine that the input to the theorem is a function f, which has a good ratio between its quadratic form and its variance. Okay, so let me write dagger for this inequality, and you should think of the input to Cheeger's theorem as this function f, which satisfies the dagger inequality in this box for like a good small value of lambda. And the desired output is this set S. We're trying to convert f to S such that S's conductance is comparably small. Good, so imagine this is our sort of quote-unquote input function f, and we're trying to convert it to this set S. And this assumption, this dagger assumption about f, is some kind of, you should think of it as like a Lipschitz condition on f, or a smoothness condition on f. Remember, this quadratic form of f is sort of like the average squared distance, or difference between s values along a random edge. Okay, so in this picture, imagine, it's particularly if you think of G as being the path graph, it's kind of the average squared difference between f values and two neighboring vertices. Okay, and so therefore, to say that it's small, as our dagger hypothesis does, at least compared to the global variance, is to say that f values doesn't change too much locally. So it's sort of Lipschitz, it moves smoothly, it doesn't have wild spikes. And now if you look at what our strategies are going to do, our strategy supposedly for finding a set S is to, we're going to pick some threshold t, and we're going to either take a super level set or a sub-level set. So perhaps we'll take a super level set. We'll take all those vertices where f's value is bigger than t, and really this is a set of vertices, so it's like maybe this set of vertices and also this set of vertices. And we're trying to show that this set S also sort of has comparably small quadratic form. And remember, what is the quadratic form of the indicator of a set S? It's like the fractional boundary size. It's the fraction of edges that go from inside S to outside S. And in this picture, it's sort of just like the, on this picture, a set S is like a collection of intervals. And so the boundary size is sort of just like the number of endpoints, 1, 2, 3, 4. Okay, so we're trying to show that this super level set or sub-level set idea for some value of the threshold t gives you a set that, is not like zillions of disjoint chunks that have like a lot of edge boundary size. It's just, one chunk that has like a small boundary size. And perhaps you can imagine that comparably, if, f, were not smooth, we're not kind of Lipschitz, if f's a Rayleigh quotient here, or its lambda were very large, maybe that means f is like an extremely wiggly function. And in that case, you might imagine that this exactly this strategy of taking a level set will not work out so well. Then you would get like some huge chunk of disjoint s's, and there'd be a very big boundary size to them. Okay, so this is sort of the idea of the proof, if you will. And now we're going to try to actually execute this proof of converting a function f with small lambda into a set S with small conductance. Okay, before we really get into it, I have to make sort of a small, without loss of generality, starting condition. As we're going along with converting this function f into the set S, there'll be a couple of stages where we'll say, ooh, I wish f had this like mildly convenient property, like is non-negative, or some other such property. And it's going to be without loss of generality, essentially, that f has these convenient properties. So in fact, let me make a definition for what these convenient properties for the proof are going to be. They're not really motivated yet, but you'll see them as they come in. So let me say that, well, let's say a function g on the vertices is quote-unquote convenient, just for the purposes of this proof, if two things hold. One, g should be non-negative, and two, this one's a little bit funnier, but we're going to look at the support of g. Okay, so the support of g is the set of vertices where g has a non-zero value. And we actually want this to be kind of a lot of the vertices. Okay, we don't want g to be like, okay, g's non-negative. We don't want it to be like everywhere non-negative. We actually want it to have like a lot of zero values. This will be convenient. And specifically, we'll request that the volume of this set, in the regular case, is the fraction of vertices where g has a non-zero value, is not that large, at most a half. Okay, so these are two convenient properties of a g, well, of the input function f that we're going to try to convert to a set. And the claim is that we can assume that our given function f is convenient, losing a factor of, let's say, a half, or 2, I suppose, in our assumption dagger about f. Okay, so what we're going to do is given our input function f that satisfies dagger, we're going to replace f with a closely related function, which is a, convenient, and b has the same inequality, except maybe up to a factor of 2 or something. Okay, and this factor of 2 will, enter into our final constant factor in our conclusion, but I was being a bit chill about that anyway. Okay, so how do we do this? How do we make a function f convenient? It's actually like basically a simple trick of the type that's often used in, again, like calculus arguments. And it'll go in 2 steps. So here's the proof, I suppose. Step 1, first translate f, i.e. add a global constant to f's values. So its median, sort of the value of f that it takes on half the time it's below the median and half the time it's above the median, so that its median is 0. Okay, so precisely what I mean by this is the volume of the set of vertices where f's value is positive should be at most a half, and also the volume of vertices where f's value is negative should also be at most a half. Okay, so basically arrange for 0 to be the value such that f is half the time less than 0, or maybe less than half the time, and half the time more than 0. Okay, you can always achieve that by adding a global constant to f, just to change its median around. And why can you do this? You can do this absolutely without loss of generality, without changing our assumption about f, that dagger inequality, at all. And that's simply because, as we've seen several times, the quadratic form of a function f and the variance of a function f are, translation invariant. If you add a global constant to a function f, it doesn't change either of these 2 quantities. Okay, so we can take f, we can make its median 0, and it doesn't change anything at all about our assumption here, this yellow rectangle assumption about f. Okay, that's a good start. And the other trick for this convenience is to split f into its positive part and its negative part. And one of these 2 guys will be the convenient version of f. So just what do I mean by this? Let's say again that I draw a picture of f's values somehow. This is v, this is r, this is f. So the so-called positive part of f is the function which it's 0 whenever f is negative, and otherwise it just equals f. Okay, so it's this thing I'm trying to draw in yellow here. This yellow is f positive. Okay, so just to repeat, this is a standard move. F positive is, you can write it as the max of f and 0. And similarly, we're going to define f negative. It's slightly funnier. I'll try to do it in like this green. So f negative, it's the same as f whenever f is negative. Sorry, that's not right. What you do is you look at the function which is the same as f when f is negative and 0 otherwise, and then you take the negative of this. So this green is actually negative of f negative. So really, f negative is like you flip this up. This is like the real f negative. Okay, I didn't explain that super great, but it's the maximum of negative f and 0. Okay, so let me take this part out. It's the negative, or the reflection of this green function. Okay, so this is a classic way to break up a function f, and the point is that f is f plus minus f negative. Okay, so the difference of these 2 functions. These 2 functions are both non-negative functions, which is great, because I said one of these is going to be our convenient version of f. So they're both non-negative, and f is the difference of them. And what I want to argue to you is that one of these, either f plus or f minus, is going to be a good replacement for f. It's going to be convenient, and it's going to basically have the same inequality assumption as f, up to maybe a factor of 2 on the parameter lambda. Okay, so one thing about that is actually easy, the fact that both of these are convenient. So f plus or minus are both convenient. And that's easy to see. On one hand, they're both non-negative. That's great. That's one of the properties of convenience. And on the other hand, this condition right here, that the volume of points where f is positive and the volume of points where f is negative are both at most a half implies the other aspect of convenience. Okay, you see, so let's take f plus, for example. We know from this assumption that this region where f is strictly positive has volume at most a half, or it takes up at most half of the vertices. Okay, and this region where f is strictly positive is exactly the support of f plus. Okay, that's the part where it's non-zero. Okay, so this condition here, where is it? This condition here exactly implies that f plus is convenient, and similarly, this condition exactly implies that f minus is convenient. Okay, so either of these, f plus or f minus, is convenient, and now let's just try to show that they both more or less satisfy the inequality that we're assuming about f. So let's see that. So recall that the quadratic form of f is a half times the expected value over a random edge, uv, of f of u minus f of v squared. It's sort of the local value, average, over a random edge of the square difference between s values at the endpoints. And what I want to claim is that the quadratic form applied to f plus is at most this. And actually, I also want to claim that the quadratic form of f minus is also at most this. Okay, and that's a good start, because remember, our starting assumption about f is that it has a small quadratic form compared to its variance. So I'm going to show that f plus and f minus have even smaller quadratic form, and then I'm going to show that one of them has a variance which is not much smaller than f's. So the thing about the quadratic form is easier. Let me just try to say it in words. What's going on here? You pick a random edge, like maybe this edge, maybe from here to here, again pretending that the graph is the path graph, and then in the quadratic form for f you look at the square difference between f's values at these 2 points. Now let's consider the quadratic form applied to f plus. Well, it's going to have the exact same expression, but with pluses here. And, one of a few things can happen in this expression depending on what's going on with s values at u and v when you choose a random edge u and v. If they're both positive, like in this picture, then you'll still get f of u minus f of v squared in your contribution to the quadratic form of f plus. So nothing changes. But other things could happen. It could be that for a particular edge uv, f's values were both negative. In that case, this square difference would be contributing positively to the quadratic form of f, but in f plus, you'd just be getting 0 minus 0 squared. So you'd be getting less in the quadratic form for f plus. Okay, and similarly, if uv is a random edge where f had one value positive and one value negative, okay, it's contributing the square difference of those values to quadratic form of f, e of f. But in f plus, one of those values gets changed to 0, so the square difference is now even less on this edge. Okay, so it's contributing less to the quadratic form of f plus. And the same argument holds for f minus. So I hope this sort of justifies in words to you the claim that the quadratic forms of f plus and f minus are only smaller than f. Okay, I want to now make a similar but slightly harder claim for the variance. Let me claim that the variance of f is at most 2 times the variance of f plus plus the variance of f minus. Okay, now I hope I got this claim right and the constant factor right. I was just working this out before recording the video, and I hope I didn't botch it. The point is, let's suppose I prove this claim. Then what does that mean? I can bring this factor of 2 over here, and then I'll get that variance of f plus and variance of f minus add up to at least half the variance of f. And so one of them has to be at least a quarter of the variance of f. Okay, I suppose I could divide both sides by another factor of 2, and I'll get that the average of this variance and this variance is at least a quarter variance of f. One of them has to be at least the average. And so I conclude that either f plus or f minus has variance that's at least a quarter of the variance of f. Okay? And so I'll pick that one to be my new convenient replacement for f. It has at least quarter of the variance, and its quadratic form is smaller. Okay, which means that it satisfies this inequality here up to a factor of 4. The left-hand side went down. The right-hand side went down by a factor of at most 4. Okay, so the lambda value changed by a factor of at most 4. Okay, so I just need to justify this little claim. And again, I'm going to kind of sketch that. Let me put all the factors back where they were. So again, similarly, if you remember, the variance of f has a very similar expression to the quadratic form of f, but with it's sort of the global variance. So this is in fact equal to half, which we don't need to worry about, the expected value over just independent random u and v of the same thing, f of u minus f of v squared. Okay, sort of the global average of f of u minus f of v squared, when these are not necessarily coming from random edge. Okay, and we have a similar expression, the analogous expression for variance of f plus and variance of f minus. And I'll just talk this through in words. We can make a similar argument to what we did before. Let's say we take a random u and v. Maybe this is somehow u, this is somehow v, and maybe f's value at u is up here. This is f of u, and this is f of v. Okay, so for each pair u and v, they contribute some quantity, some non-negative amount to the variance of f. And you see, let's say they're both positive, then in the analogous expression for f plus, we'll be getting the same contribution, because f plus will have the same value at u and v if they're both positive, and so it'll make the same contribution to f plus. On the other hand, if they're both negative, then it would make zero contribution to the variance of f plus, because f plus would have value 0 at u and v, but it would make the same contribution to f minus. Okay, so if we were to just add the variance of f plus and the variance of f minus, this would be at least the variance of f if, like, u and v were always magically had this property that f had the same sign on them. Okay, because for every pair uv, it either contribute to f plus's variance or f minus's variance, the same amount that it did to f's variance. So there's one last possibility, right, that for a given u and v, like maybe one of them makes f positive and one of them makes f negative. So how much is this contributing to the variance of f? It's contributing this height squared. That's the contribution to the variance of f. And what I want to claim is it's contributing like a decent amount to at least the variance of f plus or the variance of f minus. It's contributing this amount squared to the variance of f plus and this amount squared to the variance of f minus. And at least one of these contributions is half the contribution to the overall variance. So sort of the worst case is if, this height were h and this height were like negative h, and then the f's values were plus or minus h, and then the contribution to the variance of f would be 2h squared. That would go into the variance of f. And you'd only get contribution of h squared to the variance of f plus and minus. Okay, so when you sum up the contributions to the variance of f plus and minus, you get 2h squared, but f's variance gets 4h squared, and this accounts for the difference of the factor of 2. Okay, so I don't want to dwell on this too much more because it's really just a without loss of generality warm-up for the real proof. But finally, take my word for it, if you didn't follow all that for either f plus or f minus, we have the same assumption, and therefore we can assume that f has these two key properties, convenience. Okay, remember these two properties are that we have a non-negative function, and the volume of the support is at most a half. Okay, great. So now, it's been a lot of warm-up. We'll finally get to what I really consider the proof of Cheeger's inequality. And it goes back to this idea I mentioned at the beginning of the proof. And we're going to need a lemma, but a crucial lemma. This lemma is, in fact, has a fancy name in calculus. It's sometimes called the co-area formula in analysis, but It's pretty simple in the context of graphs. Let's assume you have a convenient function g. Actually, we don't even need convenient. We just need it to be non-negative. Okay, so we have some function on the vertices that's non-negative. That's going to be convenient, but we'll say it's non-negative. Then, okay, this is the content. The integral from 0 to infinity of the probability over a random edge uv, that this uv, I'll say, crosses g greater than t dt. Let me write the rest of the lemma and then I'll explain this scary looking quantity, is equal to the expected value over a random edge of g of u minus g of v in absolute value. Okay, that's not super clear, but I wanted to make sure I didn't go off the side of the screen. Let me rewrite this a little bit. Expected value, absolute value, g of u minus g of v. Okay, so the right-hand side is not too complicated. It's sort of like the local variance of g, but when we use this 1 norm instead of squared 2 norm like we do in the definition of the quadratic form. Okay, it's expected absolute value of the difference. Okay, what's going on with this scary left-hand side? Okay, first of all, what does it mean? So we're picking a random edge uv, and we're looking at the probability it crosses this thing. Now remember, this thing g greater than t is a set of vertices, right? It's the super level set t. It's all those vertices where g has a value bigger than t. So that's some set s. Maybe this is your whole graph. This is, g's values kind of go up like this, and this is the super level set g greater than t. To say that uv crosses it is just to say that this edge uv has one vertex inside and one vertex outside. Okay, it could go either way. So g's value is less than t on, sorry, it's greater than t on u or v, and it's less than or equal to t on the other one. Okay, so we're looking at this probability here, and then we're like integrating it over all t. This is a bit of a math trick. You can kind of mentally think of this, an integral is kind of like, a summation or an average. So you can kind of think of this as like the average crossing probability when you average over t. Not quite, but that's a good mental picture. So it's sort of like the average crossing picture probability when you pick a random t. Not really, but sort of. And it's saying that's equal to this kind of local variance of g, which makes some sense. The more g varies, the faster it shoots around, you could imagine that you have like a higher probability that a random edge will have one value on one side of t, and g will have another value, g's value at the other point will be on the other side of t. Okay, and also to just try to make this look a little bit less scary, remember a homework exercise or a well-known fact is that if you have a non-negative random variable y, then we have this simple fact. You can compute its expectation as the integral from 0 to infinity of the probability that y is at least t dt. Okay, that was a homework exercise. That's a formula you may recall. And this left-hand side is, it's doing something very similar to this fact. Okay, so a bit of a math trick. Okay, so this is going to be the key lemma. And so let's prove it. It's quite straightforward. Okay, proof. Okay, well, let's just look at this expression. I'll just rewrite it. It's the integral from 0 to infinity. The probability over a random edge, just say it in words, that t is between g of x, g of u and g of v. dt. And in fact, let's do a classic trick of replacing a probability by the expectation of an indicator. So I'm going to do that using erasing. I'll change this to the expected value, and then I'll take the expected value of this thing, the indicator random variable, for the event that t is between gu and gv. Okay, so it's a funny thing. We're like integrating over t, and so at this point t is like a fixed real number, and now we're choosing a random u and v and saying, oh, let's look at the event that gu and gv straddle this number t. Okay. Well, as always in these tricks and in this proof that the expected value of y is the integral of this whatever, or whenever in life you have like a double sum, you should exchange them. So an integral is like a sum, an expectation is like a sum. You should always exchange them when you see them. I didn't even need to check my notes to see that that was the next move. It had to be. So let's exchange them. This is equal to the expected value over a random edge uv of this integral from 0 to infinity of the indicator that t is between gu and gv dt. Okay, now let's think about this. So we have sort of now at this point in the picture, we have u and v fixed, and g of u and g of v are some numbers. So let's imagine this is the real line. Maybe we've picked u and v, and g of u is this number, and g of v is this number. And now we're integrating this 0, 1 indicator, that t, this is the t-axis if you will, that t is between gu and gv. So we're integrating this function, this step function. This is this indicator function here. This is 1. So we're integrating this function, the indicator that the parameter t is between gu and gv. Okay, so the integral is just the area of this rectangle, and it's got height 1, and its value is the absolute, sorry, its width is the absolute value of the difference between gu and gv. Great, so this quantity is equal to the expected value over a random edge uv of this rectangle's area is, as I said, it's just gu minus gv in absolute value. Okay, and that's exactly what we claimed it would be up here. Okay, so that's the end of that proof. Okay, so this little trick, this co-area lemma, sort of lets you relate like the probability that a random edge will be on the boundary of this super level set, g of t, to some kind of notion of the variance of g as a function. Okay, so the last step is we're actually almost kind of done, except that, you know, this is the variance, quote unquote variance, but where you use absolute values, and we wish that it were the variance when used squares, because, you know, that's related to the actual variance of g. Okay, so we have 2 steps to go. One step is to, you know, both these 2 quantities are sort of almost what we care about. First step is actually going to be relating this quantity here to exactly the conductance of super level sets of g. And the second step is going to be relate this to like the actual variance with squares of g. Okay, so let's try to do that. So let's start with the corollary of this co-area formula. It's going to be that, well, this right-hand side that we just saw, this sort of thing that's almost like the variance of g, is at least maybe 2 times the conductance of g times the expectation of g. Okay, remember g is a non-negative function, so this expectation is a non-negative quantity. Okay, and this is the part where we're going to relate, okay, on the right-hand side, we have the left-hand side in our corollary. So we're going to be relating this scary integral thing to the conductance. Okay, so what's the proof? Okay, so what we know is this quantity here is exactly equal to something by the lemma. It's equal to an integral from 0 to infinity dt of some quantity. And what was that quantity? Well, let's look back at it. It's this quantity. And actually, this is precisely the sort of edge boundary size of the super level set g greater than t. Remember, g greater than t is a subset of vertices. It's actually twice the edge boundary size, because in our definition of edge boundary, or our definition of like the quadratic form of an indicator, we only counted like sort of the directed edges going out. And in this probability, we're We're counting UV as crossing if it crosses either out or in. Okay, so what I'm trying to say is if you, put the definitions in appropriately, this thing we're integrating is literally 2 times the quadratic form of this g greater than t. Okay, remember this g greater than t is like the, well, here I mean the indicator function for those points where g is at least t or greater than t. Okay. So now we relate this to conductance. So okay, what we want to say is we know that for every set of vertices in the graph, their edge boundary size is at least the conductance of the set times the volume of the set. Okay, so that's the definition of the minimum conductance is phi g. And if phi g is some value, it means that every set in the graph, volume between 0 and 1/2, has edge boundary size that's at least phi g times the set's volume. Okay, so what I want to say is this is at least this quantity here, the edge boundary size, or twice the edge boundary size of the set g greater than t, is at least, I'll keep the factor 2, phi g times the volume of g greater than t dt. Okay, and this is literally by the definition of phi g. It's like the number which, sorry, it's the least possible ratio of this edge boundary size to this volume size. Okay, actually there's a slight catch here, right? In the definition of phi g, you're only allowed to make this assertion when the set itself has volume at most 1/2, right? The definition of a conductance, you only look at sets of vertices whose volume is at most 1/2 and say that they have kind of conductance at most, or sorry, at least phi g. But luckily, that's great. This is where convenience comes in, because the set of points where g is greater than t, its volume is certainly at least the volume of, it's at most the volume of g greater than 0. Okay, it's if g's value is bigger than t, it's bigger than 0. And we know by convenience that this volume is at most 1/2. This is convenience. Okay, so here we're assuming g is convenient. Okay, and so that's just so that we can make this deduction here. Great, so let me erase that. Okay, good. So now let's just write this definition of volume slightly differently. This is 2, integral from 0 to infinity. Actually, I can bring the phi g out as well. 2 phi g. It's just a constant. The volume is the probability for random u that it's in this super level set g greater than t, which is really like saying that g of u is greater than t. And now, actually, if you remember that basic probability inequality I was reminding you of, this thing is exactly the expectation of g of u. Okay, the expectation of a non-negative random variable, which g is, by convenience, is exactly this integral of the probability over t of the probability that the random variable is bigger than t. So g of u is the random variable here, where u is drawn from the distribution pi as always. Okay, and that actually also completes this proof. See, what we got was this quantity is at least 2 times phi of g times the expectation of g. Great. And so let's just rearrange this. Okay, so a further conclusion is the following. Assuming g is not constantly 0, we deduce, I'll just put phi g on one side and divide by expectation of g. Okay, I can divide by expectation of g. It's non-zero because g itself is not constantly 0. I get that phi of g is, at most, 1/2, I suppose, times a ratio. In the numerator, I have expectation over a random edge uv, absolute value of g of u minus g of v. Okay, in denominator, we just have expectation over u of g of u. Okay, and you see, this is looking quite good. If you recall way back to our original goal was to get a set S, which is going to be a super level set, that has conductance, which is somehow comparable to lambda. And what is lambda? It's the ratio of this quadratic form of f to the variance of f. And now way down here where we are, we've shown that phi of g is at most some other ratio that looks suspiciously like the quadratic form of g divided by the variance of g, but not quite. Somehow it's like there's some squares missing. If there were just some squares in there, it would look extremely good. And so a bit of a twist ending here. We're going to apply all this work we've done to conclude this, not with g being f, but with g being f squared. Okay, so like plot twist, apply this with g being f squared. Okay, so now actually there's a few things to check to make sure that this is legal. First of all, okay, we're assuming that g is not constantly 0. That's equivalent to assuming f squared is not constantly 0, which is assuming that f is not constantly 0, which is part of our assumption. We're assuming this f originally had non-zero variance, so it's not constantly 0. That's fine. Next, all along you were imagining that, oh, g is supposed to be the convenient function. So now we have to check that f squared is convenient. Now, originally I showed you it was without loss of generality to assume that f is convenient, but now I've done a little bait and switch and I want to say that, oh, I want f squared to be convenient. But actually, that's fine. I mean, we just have to look at the definition of convenience to see that it's fine. F squared is actually always non-negative, so that was one part of the definition of convenience. Where is convenient here? So f squared is always non-negative. That's super easy. And here we just need to show for the other definition of convenience, we have to show that f squared's kind of often 0. The volume of the place where f squared is strictly bigger than 0 is at most a half. But the vertices where f squared is strictly bigger than 0 are exactly the same as the places where f is strictly bigger than 0 once we make f convenient, as we did at the beginning. So we made f convenient at the beginning, so it's non-negative, so it's either 0 or it's strictly greater than 0, and by convenience, the places where it was strictly greater than 0 was at most half of all the volume. And now we're looking at the places where f squared is strictly greater than 0. It's the same as the places where f is strictly greater than 0. So therefore, this set also has volume at most a half. Okay, so great. I've pulled this little switch. I showed you that you could assume f is convenient. Now I'm telling you, therefore actually f squared is convenient as well. And so all these reasonings that we've done about g, we can apply with g being f squared. Great. So we get that the minimum conductance of g up to a factor of half, it's actually even working in our favor, but again, I'm ignoring these constant factors, is given by this ratio, and we can replace g with f squared. Okay, so, well, let me just rewrite that. Phi of g is at most a half expectation, u drawn from v of, I'll write it like this, f squared of u, it's a bit funny to write it like that, but I'll write it like that, minus f squared of v in absolute value over expected value over u of f, okay, I'll write it the normal way here, f of u squared. Okay, and now it's looking much better. The numerator is almost like the variance, except the squares are like sort of in the wrong place. We want fu minus it's almost like the quadratic form, except we want like fu minus fv all squared, not absolute value of difference of squares. But now it's just like simple math tricks. Okay, so let's do the simple math tricks. The numerator here is expected value over random edge uv, absolute value of f squared u minus f squared v. Okay, let me write it the normal way actually. F u squared minus f of v squared Okay, now I'm going to use that a squared minus b squared is a minus b times a plus b. That's a fact we all know. Put absolute values on both sides. So we turn everything here into absolute values. Okay, and I'll apply this here because we have the difference in absolute value of two squared things. So this is equal to expected value over a random edge u of v of absolute value of f of u minus f of v times absolute value of f of u plus f of v. Okay, great. And whenever you have an expectation of a product of two things and you don't know what to do Cauchy-Schwarz. So that's what we're going to do, Cauchy-Schwarz. So if we Cauchy-Schwarz, we got this is at most square root expected value over a random edge uv of, okay, first term gives us sort of exactly what we're going to want. Square of an absolute value, we can drop the absolute values, we get f of u minus f of v squared, and that's going to be glorious. On the other side, we have expectation over a random edge uv of f of u plus f of v squared. That's a little funky, but we're going to show that it's, not too big. It's not too big compared to the overall variance or squared value of f. Okay, so this quantity is a dream because it's exactly, by definition, 2 times the quadratic form of f. Okay, and finally, we can use our assumption about f, dagger, which told us that the quadratic form of f is at most lambda times the variance of f. So, hooray, we can finally use our only assumption in the proof. This is at most 2 times lambda times the variance of f. Okay? And so that's good. We've got the variance on the right-hand side here. It's been square rooted. In fact, we can even say that this is at most 2 times lambda times the expected value of f squared. The variance is always at most the expectation of the square. You might think that might lose something, but we arranged for f to have median 0, which is similar to mean 0 anyway, so it doesn't really lose much. Anyway, it's true. Over here, we're just going to do something trivial. Here's another very trivial fact. A plus b squared is at most 2 times a squared plus b squared. Okay, this is, you kind of wish it were a squared plus b squared. That's true. As an upper bound up to a factor of 2. I suppose the difference of the two sides is equivalent to a squared minus 2ab plus b squared, which is a minus b squared. I think I got that right. Okay, so that proves this little fact. Okay, so we'll plug that in here again with a being f of u and b being f of v. Okay, and we get that this thing is at most 2 times expectation u of v of f of u squared plus f of v squared. Okay, and that's kind of cool because now linear expectation tells us, remember, here u of v was a random edge, but in isolation, u has the distribution pi, and v also has the distribution pi, as we know. So this is exactly equal to 4 times the expectation over a random u of f of u squared. Okay, which is actually the same thing. I mean, we got expected value of f of squared in both places here. Okay, so finally, we're pretty much done here. Putting everything together, we conclude that this is at most square root of 2 times lambda times expected value of f squared times square root of 4 times expected value of f squared. Okay, great. So this is, I don't know, 2 root 2 times root lambda. So this is where the root lambda comes in, times just expected value of f squared. Okay, so this was our upper bound on the numerator. And take a look. Ta-da! Our denominator is also expected value of f squared. Okay, so this whole star, which is half the ratio of numerator and denominator, is, therefore, star is at most a half the ratio of the numerator and denominator. It's 2 root lambda, expected value of f squared over expected value of f squared. This denominator is the denominator. This all cancels out, and we indeed get some constant, I suppose root 2 times root lambda. But our final constant is not root 2 because of that without loss of generality convenience factor at the beginning. But it just turns it into some other constant. And we're done, right? So we just bounded, finally, the conductance, the minimum conductance, 5G, by some constant times root lambda. And let me finally just say, I'll let you take one last look at the statement of the theorem here. Right, this was our final statement, bounding 5G by a constant times root lambda. We said, give me any function f that's non-constant that has this bound on its quadratic form as a function of its variance. Then we'll pick out this set S with small conductance. And in fact, we managed to do that. If you recall how our set S eventually arose, well, you have to look back through the proof, but the key inequality came from here. This is some sort of average over t. We showed this average over t was effectively at most something, and therefore there exists a value of t where its value is at most something. Okay, so maybe I'll leave that last deduction of the proof to you, but the form of the proof actually shows that this constructive method of finding a small conductance set S given a function f with small Rayleigh quotient, it follows directly from the proof methodology.